In this video we're going to have a look at the structure of an amino acid and some of the chemistry of that structure. So what we're going to do first of all is remind ourselves of what sort of groups we're going to find in an amino acid. So the name gives us all the information that we need. Amino acids are going to contain the amine group and the carboxylic acid group. So can you remember what an amine group looks like and a carboxylic acid group? Pause the video, see if you can draw out just above the names what those two groups look like in organic chemistry. So there we go. An amine group, or in this case a primary amine group, would be an NH2, and a carboxylic acid group is C with a double bond O and then an OH, a CO group. So the alpha amino acids, or the two amino acids as the chemists would probably call them, are the naturally occurring ones, the ones that are going to be useful in our proteins and DNA structures. These are the only ones you will find. And they are called two amino acids because the amine group and the carboxylic acid group are both attached to the same carbon. So if the CO group carbon is carbon number 1, the amine group is attached to carbon number 2, and we can draw that structure out. So if we imagine we've got our carboxylic acid group here, it's attached to a carbon, and the amine group is attached to the same carbon. So if I attach my amine like that, that would be carbon number 2 in the chain. This would be carbon number 1, and this would be carbon number 2. So the chemist might call those two amino acids because the amine group is attached to number 2. 2-amino something oic acid. We've also then got, every amino acid has a hydrogen and a variable side chain, an R group, and that R group will vary from amino acid to amino acid. Different amino acids are going to have a different chain there, and you might have come across some of those if you've been studying biology. Now, one of the things that we might get asked in a chemistry exam that we wouldn't get asked in a biology exam is about stereoisomerism of amino acids. So having a look at that amino acid structure that we've just drawn, what you'll notice is that middle carbon there is chiral. It has 4 different groups. So we could take a little second and have a think about what that looks like for us. So if we were to draw, because we know when we're drawing chiral carbons that in order to show the two stereoisomers we need to draw in 3 dimensions to show that they are arranged differently in space. This is our chiral carbon at the centre, so if we go back a second to this structure, we're looking at this carbon here as our chiral carbon. So our chiral carbon, if we have a look, so this is this carbon here. Remember that the 4 groups, what were they? They were a hydrogen, an amine group, a CO group, and a variable side chain. So we've got 4 different groups, and so we could draw a non-superimposable mirror image. See if you can draw a non-superimposable mirror image. So there you go. If you have drawn the mirror image, you should see that you've lined the groups up. Be careful that we do need to maintain the good connectivity. So here the N is connected, but we're not writing letters backwards, so we don't want to invert our letters. A C still needs to be a C, not a backwards C. You'll notice at the top I've drawn the CO group in the same direction both times, and that's just easier because at the top you can do that to maintain your connectivity. So amino acids are going to have a chiral carbon. Now there is one amino acid that doesn't have a chiral carbon. So it says here the exception of glycine. So just take a minute yourself and think, do I know why glycine might not have a chiral carbon? What could the R group, that's the only bit that can change, be if it's not going to be chiral? And the reason that glycine is not chiral is because the R group in glycine is just the H. So you've actually got 2 hydrogens attached to that carbon, therefore it does not have 4 different groups. What we're going to do now is we're going to try to draw optical isomers of serine. So I want you to draw out the 4 bonds like that and draw out the mirror image like that. And I want you to use your data sheet that you've got to find what the R group is in serine. Now, the R group tends to be the longest one, so a little bit of a tip might be that if you actually put the R group up here at the top, it's the easiest one then, because you don't need to reverse the order of the atoms for connectivity purposes. So if you put your R group at the top, you should be able to draw your structures a little bit easier. So use your data sheet, see if you can find the structure of serine and draw in the non-superimposable mirror images, the optical isomers. So there you go, the R group in serine, if you look it up on your data sheet, the R group is CH2OH. So I've put that at the top. It doesn't matter where you put the 4 groups on the first structure as long as you mirror the position on your second. So again, use your data sheet and see if you can draw the optical isomers of phenylalanine. So again, find the R group. The R group is a CH2 and a benzene ring. Draw out the 2 tetrahedral structures as mirror images and then put your groups. And there we go. Optical isomers of phenylalanine. So what we're going to move on to now is just look at the properties, the acid-base properties of amino acids. Now, amino acids have both an amine group and an acid group, carboxylic acid group. Now, we know that amines are bases because they have a lone pair on the nitrogen which can accept a proton. So, amines are bases. So we've got lone pair on N accepts H+, and we've talked in our amine studies about which amines would be stronger or weaker bases. And a Q group is an acid, can donate that H+ from the end. So amino acids can be both acids and bases, and there's a word for that, that word being amphoteric, and we've studied that in a couple of other places in chemistry, the amphoteric nature of things, because they can react with both acids and bases. So let's take our amino acid structure with its variable R group and its Q group and think about why that could react. Now, amines are bases. So we're going to accept H+. So we're going to add H+. And where's that proton going to go? Well, that proton is going to attach itself to the lone pair on the nitrogen. So the nitrogen already had 2 H's and a lone pair. And we're going to put that third one on. That's going to make our amine an ammonium salt. And we've got a plus charge on our amine. So then we can look at our Q group, which is our acid group. It's going to donate H+. And what's it going to donate it to? It's going to donate it to some alkali usually. So if we take our amine group, we take our amino acid structure like that, the proton that we're going to donate is this one, remember? We're going to, if we donate it to a base, then we can see what's going to happen. We're going to end up with the amine staying as it was, because that didn't react. And we're going to end up with a C. And if we drew this out, where is the minus? The minus is actually on the O, because that's where the proton fell from. And we've made some water. So there's our proton from our acid attaching to our OH to make H2O. if you can have a go at these two examples of a reaction, and this time there is a counter ion. So there is a chloride ion and there is a sodium ion in these two equations. So using phenylalanine, I'm going to pause the video, you pause it and see if you can do it yourself. Reactions with hydrochloric acid and sodium hydroxide. So there you go. I've accepted a proton from the lone pair on the nitrogen, and the spectator ion, the chloride ion, is just up there floating. And then with our sodium hydroxide. There you go. I've used some colours so you can see where everything's ending up. So the amino acid, the phenylalanine, is a proton because it can donate this red proton, this red hydrogen with a positive charge, to the hydroxide of sodium hydroxide to make water. Over on the right hand side here we've got the water with the red proton from the carboxylic acid, and the salt of the amino acid, the COO minus, is going to become a sodium salt because we use sodium hydroxide. Had it been potassium hydroxide, there would be a K plus over here. So that ends our little video on the structure of amino acids and their acid-base properties.